Oh no. Hey everyone, welcome. So you guys have now had some basis with and some work in general with operations with matrices, right? So you did some basic operations, addition, subtraction, multiplication, and scalar multiplication, right? So we're going to extend upon this and we're going to talk about what a determinant is and what it's used for and how it's found. Our focus is going to be on 2x2 matrices. Okay, so this is what we refer to as a square matrix, right? If it's 2x2, if you have a shape that's 2x2. So yes, a 3x3 matrix would be a square matrix. A 4x4 matrix would be a square matrix. So we could do this we could find what we're referring to as the determinant for any square matrix. But our focus in this lesson is going to be on 2x2 matrices. So we're going to define what a determinant is, understand its purpose and notation, right? So that's one of the really important pieces where we could give you a notation and you need to know what it means, right? You need to know that that's indicating to me I have to find the determinant and successfully calculate it for a 2x2 matrix. Alrighty. So before we get too far into this, I want to talk a little bit more about what a determinant is before I show you how to find it. So the determinant is a scalar value. So you're going to get a number for this, a scalar value. And some of this is a little bit beyond where we'll go with this, and this stuff will come up later. And we're just, as we've said before, learning like the skills behind matrices so that you can apply it if needed or wanted later on. But I still want to give you this basis. So a scalar value that can be computed from the elements of a square matrix. That's really important. If it's not a square matrix, it's not there. We're not calculating the determinant. It contains certain properties of linear transformations described by a matrix, right? So this is something, this idea of these linear transformations as they relate to matrices is going to come up more, I guess actually in pre-calculus for you guys. The determinant of a matrix is denoted these different ways. Okay, so determinant of A, or wow, that looks just like absolute value, right? That means determinant. If you see something that has this or says this, that indicates that we have to find the determinant. It's not a, let me raise my hand and say, did you forget to add the little lines? Right, so that indicates that notation is find the determinant. That's the command there. It can be viewed as the volume scaling factor, and here we go again with the linear transformations described by a matrix, a scaling factor, right? It can tell you, is it being dilated? Is it stretched a certain way? Is it reflected? Oh, that kind of relates to this. The determinant is positive or negative according to whether the linear transformation preserves or reverses the orientation of a real vector space. You haven't learned about vectors yet, right? Vectors will come for us in pre-calculus, and that's when we will come back to matrices next year. This is also huge in like linear algebra. So if it's positive versus if it's negative, telling you like, is it a reflection? Is it in a different quadrant? What happens to that vector? Think of a vector almost like as a ray. Every square matrix has a determinant, but non-square matrices do not. If every entry in a matrix is 1, the determinant is undefined. If every entry in a matrix is 0, then the determinant is undefined. We'll talk about what that means. So the determinant can help us find the inverse of a square matrix. If the determinant of a matrix is 0, there is no inverse matrix. Okay? There is no inverse matrix. This would happen if one of the rows of a matrix is a scalar multiple of the other. We just did something like this in our last unit of study. If one of them was a scalar multiple of the other, we talked about this with the lines, right? And systems. That means that you have dependent systems, right? So there is no inverse because it's like, think about it almost like as like you have the same line or you have the same plane. Since we're doing 2 by 2, like you have the same line. There's not going to be an inverse because the inverse is just that line. So if you have a determinant that is 0, that means that one is a scalar multiple of the other, right? Like I would have to multiply both parts by it. It would give me the other one, right? So like both and all the entries. So think of like if you had something like this, 2, 4, 4, 8. You don't know how to find a determinant yet, but if I told you to find, if this was A, and I said find the determinant of A, looks like absolute value, so you got to remember and shift your thinking to, we're talking about a determinant. You're going to get a determinant that is 0, and that means that there is no inverse because these are the same lines. It's a dependent system. So if we take a look, and this again is going to be, you guys have access to this PowerPoint, so you are more than welcome to like play around on this. This is a little bit, I'm going a little bit like out of AAF for this, but I still thought it was an interesting thing to show. So these here are vectors, vector V and vector U. You are not responsible for knowing anything about vectors. I just wanted to show you. We don't yet know how to calculate a determinant, so I'm going ahead on this. But the determinant of a 2 by 2 matrix. So it's a scalar, right? So like this has a determinant of 28. Let's say I would start with 1, 0. This is almost like, think about it like the parent function. And 0, 1. That's what that looks like, right? That has a determinant of 1. And then I'm scaling this in different ways. So like you can see, and what happens if I stick a negative in? Oh, it reflected. Oh, I've got a negative determinant. Right? What happens if I make this one negative also? Oh, it's like a rotation or a reflection over X and a reflection over Y. Maybe this rings a bell from some of the stuff you did in geometry last year. What if I changed this to be 2? Oh, you can see like it got scaled, right? If I multiply them both by 2, it's going to stay, remember, similar figures, right? So you can kind of see, and you can see like what's happening with the determinant. Isn't that the area of this, in this case, square? If I make this one 3, oh, it's 6. It's the area, right? If I make it a negative 3, it's going to be negative 6. I know it's a little silly. You don't really have like a negative area, but it tells you that it's no longer in that original quadrant. So think of like that 1, 0, 0, 1 almost as like the parent function. Right, so kind of interesting. So you guys have a link to this if you want to play around with it and see, but you can see like the area of the parallelogram. If I change this number too, you can see what happens. Look at that, it didn't change. Right, if I change this one also, now it changed it. Right, so you can play around with it and see. We do more with, I mean, we haven't learned vectors. Vectors will come in pre-calculus. So you'll learn more about this, but it's kind of interesting to see like where it ties in and how it ties in with geometry as well, and how nothing we do ever goes away. Okay, so that's some like information about determinants. So you're probably wondering like, how do I calculate this? Right, so finding determinants of matrices. So this notation again indicates to us that we are finding a determinant. That's what these bars mean. Right, so this is, I'm not talking about here's the matrix, this is telling me to do an operation. It's like how you're used to seeing an addition sign and that means that I have to add it. I shouldn't just leave it, right? And that's different than it being a subtraction sign. It is a notation. Okay, so notice the different symbol. The straight lines tell you to find the determinant. So to find this determinant, I'm going to multiply. This is the main diagonal. I'll write some notes. This is the main diagonal. What's the other one called? I'm forgetting the name of the other diagonal now. All right, so 3 times 4, and then I'm going to subtract the other diagonal. Negative 5 times 2. So you get 12 minus negative 10 would be 22. Right, so you can imagine, and maybe I can even go back and do this, the area of this rectangle. Think about these as points. So 3, 2, negative 5, 4. 3, 2. you're not responsible for this part. You just need to know how to find it, but I know some of us want to know more about like why it works. -5, 4. Right, so there's what that looks like. And oh, the area of this parallelogram is 22. And this is what it looks like. So you can see like the 3, 2, I'm just going here. 3, 2. -5, 4. And from that, creating that parallelogram, that quadrilateral, and the area of that quadrilateral is the determinant. Pretty cool. So really what you're doing when you're finding a determinant, here's where my letters are. So it's A, B, C, D. So it's AD minus BC is what you're doing here. All right, that's how you find the determinant. And remember that notation. So the determinant of a square matrix given a, oh, I just did that, didn't I? Given a general 2 by 2 matrix, A, B, C, D, the determinant of the matrix is AD minus BC. Okay? So again, their notation, pay attention to it. Like I'm going to keep emphasizing that because that is important. You got to know, like when you see it, that it's asking you to find that scalar. It's not asking you to do some other operation. Okay, let's do a practice. Evaluate the determinant of the matrix. So 1 times 5 gives you 5. 3 times 2 gives you 6. 5 minus 6 is -1. Right, so your determinant, and remember, get yourself in the habit of showing your work. I don't need this step necessarily, but show us where you're going here. Right, like what is your work? Show your work. You should be in the habit of this and not just showing your final answer. Show your work. Get yourself in that habit. So I would, if I were you guys at this point, pause the video. There's not a ton that I want to do with this. It's pretty straightforward as far as like the algorithm and the process for finding it is. I wanted to spend more time talking about what it is and what it can be used for. So evaluate the determinant of A. There's a notation, right? So -6 times 2 minus 3 times -4. -6 times 2 is -12. Plus 12 gives you 0. Oh, do you remember what this means? I'm going to star this. If you get a determinant of 0, hopefully I did my math right, that means that this matrix, so matrix A, has no inverse. Right? So watch this. So -6, 3, -4, 2. To get from here to here, I must have to multiply by 2/3. Oh my gosh, and I have to multiply this by 2/3 and this by 2/3. Right? This one, these are just scalars of the other. And that's why you're determinant for both parts, both columns. So if we were to go back to that graph, let's just see what that looks like for fun. -6, 3. And -4, 2. Oh, it's just a line, right? I don't have a parallelogram. Isn't that interesting? It's just a line. One is just a scalar of another. One just goes like it just radiates a little bit further. Pretty cool, right? And then evaluate, right? So again, this tells us, oh, I've got these bars. That means that I need to find the determinant. So -2 times 7 minus, and maybe you are circling, maybe you're somebody that uses highlighters and you like different colors, great time for that. 8 times 3. So this gives us -14 minus 24. No calculator needed. That gives us -38. Oh, it's negative, right? That must mean it's not in quadrant 1 anymore. I mean, you can even think about, now that you've looked at it a little bit, you don't know vectors yet, but it's just, think about this, -2, 7. Oh, I've got a vector that's like, oh, that's not, certainly not -2, 7, but that's fine. And then 3, 8, I have a vector that's going over here. So I end up with like this. This is not -2, 8 at all. But that's okay. You can see that there was a move that occurred. Okay. So in this lesson, I didn't do a ton of examples. I feel like you're multiplying and subtract. You're finding the difference of the product of the diagonals. And I think the big one was that I wanted to talk about what a determinant is and what it can be used for. I didn't go too far in depth. You're more than welcome to do some research as well, but I wanted to give you some insight into it to understand its purpose, and its notation was huge, and then successfully calculate 2x2 matrices, the determinant of 2x2 matrices. Keep in mind that this can only be done for square matrices. We are going to do it by hand for 3x3 as well, but it is a little bit more involved. And it's important that you know how to do it for a 2x2 matrix before we get to 3x3. Okay, so make sure that you're doing some practice and ask any questions you might have, write them down so that when we come back together, you can ask them. And we will see you next time. Thanks, everyone.